Hey there. Welcome to Real Analysis. This is just sort of a short little bonus video where I want to show you how you can use some of the machinery we've been developing in our chapter about sequences, namely the monotone convergence theorem, to give kind of a derivation of the existence to a number that you met in calculus or maybe even pre-calculus. That number is Euler's number. It's almost always denoted by the lowercase e. It's a transcendental irrational number, so it has no finite decimal approximation. The first few decimal places of it are 2.718. So it's kind of a ubiquitous constant like pi. It shows up in all kinds of places, exponential growth problems, continuous interest problems. It's the base of the so-called natural logarithm. All right, so what I want to do in this video is show you how you can use some of the machinery we've been developing in our chapter on sequences to sort of give the a derivation of the existence of this number. Maybe one way to answer the question, well, where does this number e come from? All right. So our primary tool to kind of analyze the sequence that I'm going to define below is the binomial theorem. I'm not going to prove the binomial theorem in this video. I hope you've seen it before, but I'll just kind of say how I'm going to use it. What the binomial theorem tells me how to expand the nth power of the sum of any two real numbers, so a plus b to the n. And when you expand such a product, well, you're going to get products of a's and b's. The number of them in total is always going to be n. So you're going to be able to group them into powers of a times powers of b. And the coefficient of that product, a to the n minus k times b to the k, is this binomial coefficient, n choose k. All right, I've got a definition of n choose k down here. It's n factorial over n minus k factorial. And you can simplify that fraction if you cancel n minus k factorial with the last n minus k terms in the numerator, then you get this expression that I've written here on the right, and that's kind of the form that I'm going to be using it in the video below. All right, maybe just to write out a few terms of this, let me kind of move this as far over to the left as I can so I can write some terms. So if you start with, say, k equal to 0, right? So the coefficient is going to be n choose 0, which can certainly be simplified using the formula below. It's equal to 1. And every one of the terms would equal a, or factors rather, would be an a, and there'd be no b's. So the first term is just a to the n, if you like, if you want to simplify that thing a little bit. And then you continue along. The next coefficient would be n choose 1 times a to the n minus 1 times b to the first, right? You can simplify that n choose 1 is n. So you have n minus 1 factors of a and 1 factor of b, and then you continue along. Each subsequent term, the exponent on a lowers by 1, while the exponent on b is increasing by 1 because they always add up to n. The number of factors total always has to be n of them. And then these binomial coefficients continue to grow. All right, so if we just sort of write the last one, I think it's all I have room here. By the time k gets to equal n, you'd have n choose n. At that point, you'd have no a's left, and you'd have all of the factors equaling b. So if you continue along this thing, n choose n is also 1, and then you have no factors of a at all, and all factors of b. So this is sort of the general way to expand binomials, right? When you learned in high school algebra how to find, say, a plus b squared, it's just a special case of this binomial theorem when n is equal to 2. Maybe you learned how to expand a plus b cubed and so on. So this is the sort of general story, right? So maybe if you want to, pause this video and kind of write down this binomial theorem, or just rewind the video to refer to it, because I'm going to be using it down below. Okay. So here's the main definition of the sequence I'm going to be using. I'm going to define a sequence called E sub n. And the nth term of E sub n is given by this expression that I've got written down over here. So E sub n is 1 plus 1 over n raised to the nth power. Maybe you recognize that expression. Certainly this probably came up in one of your calculus classes, or if you've ever studied continuous interest problems, this is sort of an expression arises naturally there, but we won't go into all of that here in this video. I'm just going to kind of approach it like, okay, I'm interested in this sequence, 1 plus 1 over n to the n. N is any natural number. And basically, the main proposition, if you like, in the lecture or in the video is I want to try to convince you that that's a bounded increasing sequence. Okay, so if that's a bounded increasing sequence, then our monotone convergence theorem says that it is going to converge to some real number E. So that's the kind of purpose of the lecture. Is if I can show that proposition, and then I combine that result with our monotone convergence theorem, well, it tells me that there has to be some number, which I'm going to suggestively call E, that's the limit of that sequence, because every bounded increasing sequence of real numbers converges. That's exactly what the monotone convergence theorem tells us. So the rest of the video lecture is going to just be showing these two properties. We're going to start with the increasing part. I'm going to try to convince you that that sequence En is increasing by just literally looking at the nth term and the nth plus first term and trying to convince you that the nth plus first term is bigger than the nth term. And then when we have that done, we'll turn around and try to convince you that the sequence is bounded, and in particular bounded above. If it's an increasing sequence, we just have to worry about it being bounded above. All right, so that's kind of the outline of our program here. So let's get going. So to start to prove our proposition, I'm going to apply that binomial theorem to this binomial expansion, to this binomial. The terms E sub n, they are nth powers of the sum of two real numbers. Yeah, if you want me to match the notation of the theorem, well, the number a is equal to 1, and the number b is our 1 over n. So b certainly depends on n, but for E sub n, that's fixed. Yeah, and let's just say right here that in that, again, using the notation of the theorem, any power of 1 is going to be equal to 1. Right, so that's going to kind of simplify the formula immensely. And then, well, the bth power of k, since it's 1 over n, is just going to be 1 over the kth power of n. Right? So that's kind of what I've written in the bottom line down here. I'm looking at the nth term, and I just expanded it, with the binomial theorem. So where does this 1 come from? Well, like what we wrote above, it would be the binomial coefficient n choose 0 is 1. And then I get 1 to the n times b to the 0. So that's just 1. Here's my second binomial coefficient. That's my n choose 1. I'm using the simplified version of it. Again, all the powers of a aren't there, so this is my b to the 1. This is my n choose 2. Every power of 1 is 1, so this is b squared, and so on. Okay, so that's what I've got here. Here's my n choose 3, b cubed. All the way to the n, this is n choose n. I'm purposely writing it out in that form. It's certainly equal to 1, but then I would have my b raised to the nth power. All right? So basically what I'm going to do in each one of these terms, by a term, of course, I just mean a term in the sum, there's a cubic expression, and then the one I'm highlighting in general, it's the powers would be k. K goes from 1 to n. But let's look at this one. There's a cubic expression of n in the numerator, and there's a cubic expression of n in the denominator. And I'm just going to do a little bit of algebra to simplify that expression. So that is, in each one of those terms, I'm going to take the k factors of n in the denominator and take them and divide them into the k factors in the numerator and simplify it. Okay, so some of these things I don't really have to simplify at all. The first one is just a 1. I think it's pretty clear how to see that the one and only factor of n in the second term cancels. So that's where I get this 1 down there. But now let's just kind of carefully talk about the second one and the third one, and I think the rest of it will make sense. So what am I doing? I'm taking these two factors of n squared in the denominator, and while I'm going to divide them into the two factors in the numerator. One of them cancels completely, so n cancels n, and then when I divide n minus 1 by n, I can write that expression as 1 minus 1 over n. All right, so canceling the two factors of n in the denominator into the two factors in the numerator produces this second term, or this third term, I guess. It's when the counter is equal to 2. All right, so continuing along the same way, here, do it for the cubic. Maybe stop the video and do this yourself. You have three factors of n down here. One of them cancels that n, And when you divide one of them into n minus 1, you get 1 over n minus 1 for the same reason as the previous term. You cancel the remaining factor of n into n minus 2, and you get 1 over 2 minus n. All right? So you just proceed down that sum, term by term, writing that simplification. The coefficients, the factorials in the denominator stay there. So in the last term, I would have 1 over n minus 1 factorial. And then I take those n factors of n down here, canceling them into each one, or not canceling, but dividing them into each one of the n factors in the numerator. And that would give me this expression that I have down here at the end. All right, so maybe this would be a good place to pause the video and sort of just kind of, balance out all that algebra on your own. Good. So this is kind of the fundamental expression that I'm going to be using for E sub n. All right, so we don't have to recapitulate the entire conversation. We can write down what would the expression look like for E sub n plus 1. Well, when the counter is n plus 1, we're going to just kind of do the same thing. The number of terms, I'm going to say this again below, but maybe I should say it right here. The number of terms total in En is n plus 1. Yeah, so there's going to be one additional term in the expression for En plus 1. And then the algebra would be the same everywhere, except instead of having these denominators 1 over n, they're going to be 1 over n plus 1s. Okay? So I've kind of lined these things up. I'm going to be calling them corresponding terms, but this is sort of with respect to the counter in the binomial theorem. This is when k is equal to 0. This is when k is equal to 1. This is when k is equal to 2. Okay, maybe I'll even kind of write a few of those in there permanently. So let me just sort of write here. This is k equals 0 terms in those expressions. This would be k equal 1 terms. Here's our k equal 2 terms, and so on. K equal 3. Here's when we get to k equal n, right? But the expansion of En plus 1 has this additional term. It's got this additional term because in the binomial expansion for En plus 1, k is allowed to take the value n plus 1, whereas in En, the largest value of k would be equal to n. So those red vertical lines, I'm going to be kind of calling those corresponding terms in these expansions. All right? So let's make some observations about these corresponding terms. I've got 4 of them down here that I've kind of just indicated with these 4 bullet points. The first one is just sort of for purposes later that En plus 1 is at least 2. In fact, En plus 1 is E1. E1 is equal to 2. So this is just going to be part of my machinery to establish a lower bound. So that first bullet point is kind of trivial, and for that matter, right now we can safely kind of ignore it. Okay, the second one I've already commented on, that En plus 1 has n plus 2 terms, whereas En has 1 fewer. Okay, we've already commented on that. Now, let's look at each of those corresponding terms. Okay, so the red lines, each of the corresponding terms. So I claim that the corresponding term in En is smaller than that in En plus 1. Let's just pick one and look at this. Okay, it's written down there why it's true in general, but I think it's easier for me anyway if we just look at one of them. Let's look when the k value is equal to 3. All right. So why is that term in En less than the term in En plus 1? Well, they certainly both have the same kind of coefficient, right? 1 over k factorial in general, or down here, I guess I'm calling it a j. And then 1 minus 1 over n is less than 1 minus 1 over n plus 1. Well, because 1 over n plus 1 is less than 1 over n. So when you subtract them from 1, subtracting the bigger quantity is going to make a smaller number, right? So that's kind of what I'm writing down here in general. For any j between 1 and n minus 1, 1 minus j over n is going to be less than 1 minus j over n plus 1, because this fraction is smaller. So subtracting something smaller results in a bigger quantity, okay? So if factor by factor in that term, you're smaller, well, then the product of them will be smaller. So that's how I establish this third bullet point. Okay. So in the corresponding terms, if I just point at them, and well, yeah, maybe I need to fix my subscripts here because the first two terms are of course equal. The first two terms are of course equal. So I don't even mind if there's a problem with my indices, I don't even mind putting a less than or equal to there. That's good enough for me. Uh, okay, so looking at them with that small repair, then yeah, this term in En is less than or equal to that one. This term in En is less than or equal to the corresponding. Same for all of them, up to when you get to the k equals nth. All right, but now there's one additional term in En plus 1. It doesn't have a corresponding term. It's highlighted in green above. And I just want to point out that that number is a positive number. So the last term, the n plus second term in En plus 1 is a positive number. Well, why? Because all of these things that I'm subtracting from 1 are less than 1. So all those factors are positive. 1 over n plus 1 factorial is certainly positive, right? So if you couple all that together, for the corresponding terms, the En plus 1 are at least as big as the Ens, but then En has some additional term that's positive. Okay, so if you roll all of that together, what do we have? It shows that this is an increasing sequence. En plus 1 is strictly bigger. I mean strictly bigger than En, because the corresponding terms are greater than or equal to, but En plus 1 has this additional term. Okay, so for every n, En plus 1 is strictly bigger than En, so we've got an increasing sequence. That's one of my main goals. This sequence is increasing. Since it's increasing, and we already said that the first term is equal to 2, well then the sequence is bounded below by 2. So I want to show that it's bounded, so we're kind of halfway done. We've got a lower bound. All right, maybe a good place to pause. I'm just going to continue so that the video is not too long. Okay. So now, how are we going to establish this upper bound? Well, we just kind of have to play around a little bit. All right. So I'll let you read, but if you take a j between 1 and n, all right, then this number 1 over j, sorry, 1 minus j over n, my tongue is tripping up here, is never going to be any more than 1. That's because j over n is less than or equal to 1. So when you subtract it from 1, you're going to get something smaller. Well, actually, j over n is strictly less than 1 because j can't be 0. Okay. Another little fact, it's going to seem a little bit out of a hat, but you'll see why. The j minus second power of 2 is not going to be more than j factorial. And to explain that to myself anyway, I just kind of write out the factors, right? 2 to the j minus 1 just means multiply 2 by itself, j minus 1 times. I've got the definition of j factorial over there. It has j factors. The first one is a 1. So if you look at the kind of quote unquote last j minus 1 factors, well, then they're greater than or equal to the corresponding factors in 2 to the j minus 1, right? 2 is less than or equal to 2. 2 is less than or equal to 3. 2 is less than or equal to 4, and so on, right? Okay, so that's what establishes that inequality. And if you flip that inequality over, you reciprocate it, well, then the inequality would reverse. So 1 over j factorial is less than or equal to 1 over 2 to the j minus 1. All right, so now let's go back to our expression for En, not counting E1, which is equal to 2. If you want to make this n greater than or equal to 1, then just make that greater than or equal to. But here I'm taking that expression that we had for En above. Here's the two ones. They look familiar. But then starting in that third term, I'm going to exploit this fact that if I replace the 1 over j factorial with the corresponding power of 2, then I only make the result bigger. And then for that matter, replacing those factors in the expression for en, since they're all strictly less than 1, if I replace them with ones, I make something strictly bigger, right? So I'm just going term by term and making those replacements. I'm replacing all of the factors, 1 minus fractions, with a 1. That makes it strictly bigger. I'm replacing the reciprocals of the factorials with these powers of 2. Those are greater than or equal to. So that's what justifies these things. All right. Now I'm going to lean on some calculus formula. This thing is a, well, actually, sorry, I put the bracket in the wrong place. This is the nth partial sum of a geometric series, 1 plus a half squared, and so on, up to 1 over the nth minus first power of 2. So you can check out your calculus book that sums up to this expression that I've written there. I tried to write it in a form that might remind you of that formula. All right. And then I'm just doing the arithmetic there. If you kind of work out what that expression looks like, 1 minus a half in the denominator is a half. So that brings out this 2. And you get this 1 over 2 to the n. All right. But again, 1 over 2 to the n is a number that's less than 1. So if I just drop that factor, replace it with a 1, that would make the result bigger. And finally, maybe the part that I understand the best, that 1 plus 2 is equal to 3. Okay, so you can stop that and kind of absorb it at your own pace, but this is the punchline. Starting at n equal 2, our sequence terms are between 2 and 3. Again, if you want to change this to n greater than or equal to 1, the only thing that's going to happen is that the first term of this sequence is equal to 2. So we've shown that en is bounded and increasing. Okay. Started off with the increasing part. We just got the bounded part. So this sequence, it's bounded and increasing. So like we said before, the monotone convergence theorem says that there has to be some number in the real numbers, I'm calling it E, that this sequence converges to, right? And we've even learned something more. The limit of this sequence would be strictly bigger than 2 because the sequence is strictly increasing. And taking the limit, we know that the limit could be no more than 3. So this sequence converges to a number between 2 and 3, but it has to be strictly bigger than 2. Okay, so now I would encourage you with a calculator, spreadsheet, I don't know, whatever software you like, Python, you should kind of numerically investigate this convergence. It turns out it's not really all that fast. Here, I did it with Mathematica. I'm going to end this video by kind of displaying my table and kind of trying to talk you into it. So I hope the table looks like it makes sense. I've got some columns here where I'm just writing down the value of the index n, and then in the right column, I'm writing out the decimal approximation. I think I chose, I don't know, 10 decimal places or 9 decimal places for the values of E sub n. So like we said above, E sub 1 is equal to 2, and then so on. So and you're looking at this convergence, you can just kind of read down the tables and sort of see like, well, when did the digits stop changing? And it's kind of tempting to say that it starts off at 2.6. Here, by the time we look at the 20th term, got 2.65. Yeah, but that 5 will eventually change here. The second decimal place, I mean, the 100th place, when you get to n equals 23. You kind of know, I wrote it at the beginning of the lecture, that the value of E is 2.718. So these actually, even by the 40th term, we're not even getting things accurate to within a tenth. It's still 2.6. It rounds to 2.7 to the nearest tenth. Yeah, so the convergence is quite slow. Looking at the first 40 terms of this sequence, our sequence value is about 2.68. Blah, blah, blah. So now I've jumped. Please notice here that I jumped out. I got impatient and I wanted all this to fit on one slide. So I jumped out to the 401st term. Okay, well, there we're starting to see the 2.7, 2.71. Yeah. Look at 20 more terms. These columns are 20 long, so 2.715. So even here, still by 420 terms out in this sequence, I have 100th decimal place accuracy, but not thousandths. right? If my calculator is correct, and E is about 2.718 something, something, something. All right. So then I went for like a quantum jump here. I got super impatient. I went out 22,000 terms past the top row of the third column. So I'm looking at the sequence terms where n is 22,401. And now, if you get out your calculator, this thing is starting to look, at least to the accuracy that I've ever memorized, at 2.718. All right. And you can kind of check. So my point is here that the sequence converges to this number, E, and I'm kind of pretending like I independently somehow know E's value. And then, yeah, just to say that the convergence is actually not super fast, right? 22,000 terms out in the sequence. Okay, so I hope that was an interesting application of the monotone convergence theorem, and thanks for listening.